Today is day 4 of Unit 9. We started today. We just checked homework today to start. We didn't have a warm-up today. So just if you weren't in class, get an answer key, check your answers for the homework. And then we just started with notes. So the first thing you want to add to your notes is the definition of mutually exclusive. So events are considered mutually exclusive when they cannot happen at the same time. So events that cannot occur at the same time. So then not mutually exclusive events are events that occur at the same time. So let's take a look at a few examples. So if I'm rolling a die one time, I have to determine if the events are mutually exclusive or not. So rolling a 2, rolling a 3. Well, those two events cannot occur at the same time. Therefore, they are mutually exclusive. On the other hand, rolling an even number, rolling a multiple of 3, well, some even numbers are multiples of 3. So those events occur at the same time. Therefore, they are not mutually exclusive. Next, rolling an even number, rolling a prime number. Well, there are some even numbers that are prime. So that is not mutually exclusive, or they are not mutually exclusive because they can occur at the same time. Last, rolling an even number, rolling a number less than 2. Well, no even numbers are less than 2 on a die, so that means that these are mutually exclusive. They can occur at the same time. Okay, so next you're going to want to put this formula into your notes. If you have two events and the events are mutually exclusive, meaning they cannot occur at the same time, then all we have to do is add the two probabilities together if we're looking for the probability of the first event or the second event. On the other hand, if the events are not mutually exclusive, meaning they can occur at the same time, then and you want the probability of A or B, you cannot just add the two probabilities together. What you have to do is add the two probabilities together and then subtract the probability of both events occurring at the same time. I like to think of this as the overlap section. So when events are not mutually exclusive, that means that there's some parts that occur in both groups, the first probability and the second. So you want to subtract away that excess because you don't want to count it in both groups. And hopefully that'll make more sense when we start to look at an example here. But so if I'm rolling a die, I want to find the probability of a 2 or a 3. Well, 2 or a 3, we said in the last problem that those two events are mutually exclusive. So mutually exclusive means I just add the two probabilities together. So 1/6 is the probability of a 2 plus 1/6 is the probability of a 3. Gives me 2/6, which simplifies to 1/3. So simple as that. Okay, and we've been doing problems that are mutually exclusive for days now. This is just a review or a review of the terminology. Next, even number or a multiple of 3. Well, we said even number or multiple of 3, those are not mutually exclusive, which means they can occur at the same time. So if they're not mutually exclusive and I'm looking for or, I am going to add still, but I have to subtract away the excess or the overlap section. So let's talk about what that means in the context of this problem. I'm going to first add the probability of even numbers. Well, even numbers on a die are 2, 4, and 6. So that's 3 out of 6. I'm going to add that to the number or the probability of multiples of 3 on a die. Well, multiples of 3 on a die are 3 and 6, and that makes 2 out of 6. But the issue with that is, think about these numbers, 2, 4, and 6, and 3 and 6. Well, I counted 6 in both groups. So 2, 4, 6, and I counted 6 here with 3. So the reason that we have to then subtract away the overlap or the probability of both events, A and B, occurring is because I don't want to count 6 in both groups, in both probabilities. So I have to subtract away the probability of A and B. What that means is, what's the probability of both even and multiples of 3? Well, in this problem, even and multiples of 3, that would be the number 6, because 6 is a multiple of 3, but it's also even. And so of those 6 numbers, one number, the number 6, meets both of those events, or A and B. So that's 1 6. So that's what I have to subtract away. And when I do that, 5 6 minus 1 6 gives me 4 6, which simplifies to 2/3. So that's my final answer for that. Now, I told students in class that you may either use the formula like I just did, this probability of A plus probability of B minus probability of A and B, or you can just think logically. So if you're thinking logically, even numbers, I would write all the even numbers, so 2, 4, 6. Multiples of 3. Well, multiples of 3 we know are 3 or 6, but I already have 6 written, so I'm just going to add 3. I'm not going to add 6 since it's already on my list. Then I'm going to count 1, 2, 3, 4. There are 4 numbers out of 6 for 6, which is 2/3. Okay, so you don't have to use the formula, but sometimes the formula actually is easier to use. So you can either use the formula for when they're not mutually exclusive, or again, just logically. And this would be my work, showing 2, 4, 6, and 3, and that's 4 out of 6 numbers. Same thing here, even number or prime. Let's use the formula first, then let's use logic. So even number, 3 out of 6. Prime, now remember, we talked about this yesterday. Prime numbers are not, 1 is not a prime number, okay? Because the definition of prime is its only factors are 1 in itself. Well, 1 doesn't count because its only factor is 1. So everything except for 1, that has only 1 in itself as factors. So 2 we know is prime, 3 we know is prime, and 5 we know is prime on a die. So that makes 3 out of 6. Okay, but then I have to subtract the probability of both even and prime. So let me think of those numbers I just listed. I said 2, 3, and 5 are prime, and of those numbers 2, 3, and 5, one of them is even, the number 2. So I have to subtract the 1/6 probability of both even and prime. And when I do that, I'm getting 6 6 minus 1 6, which is 5 6. Okay, now logically speaking, I'm just going to list these even numbers, 2, 4, 6. Prime, 2, 3, 5, except for I already have 2. So 3 and 5. Now I count 1, 2, 3, 4, 5. 5 out of 6. 5 out of 6 is the probability. Last, even number or number less than 2. We said in the previous problem that even number less than 2, those are mutually exclusive events. So I just find the probability of each and add. So even number, that's 3/6. Number less than 2, that's 1/6, because there's only one number, 1. And when I add those, I'm getting 4 6, which simplifies to 2/3. Okay, so that takes care of mutually exclusive and not. Now you're going to need to turn in your packet to page 14 and take a little bit of notes here on page 14 on independent versus dependent events. So about halfway down the page, you'll see independent events. Let's put the definition there. So independent events mean that when the occurrence of one event does not affect how a second event can occur. One event does not affect a second event is independent. Dependent, on the other hand, when the occurrence of one event does affect how a second event can occur. One event affects the outcomes of a second event. And we're going to look at a couple examples here, but I also talked about, we did some problems yesterday in class, And if you recall, the one page was all independent events. And just one example from that page, if you recall the problem where you were picking energy drinks and you picked an energy drink and then you put it back and then you picked a second energy drink, well, you put the first one back. So picking the first one didn't really affect the second one because you put the first one back, so you still had the same amount of energy drinks and the same types of energy drinks that you did for the first pick. So that was an example of an independent event because you put the first one back. So picking the first one didn't affect the second pick at all. Looking here, these events, are they independent or dependent? Rolling a die, flipping a coin. Does rolling a die affect my flips for a coin? No. Therefore, these two events are independent. Picking a card from a standard deck and not replacing it, then picking a second card from the deck. Well, if I pick a card from the deck and I don't put it back, that means there are less cards in the deck. So my second pick would be affected by my first pick because I didn't put the first card back. So in this case, these events are dependent. The first pick affects the second pick. Now, had we put the card back, then we'd be talking about independent. Okay, so we already have done problems where we've had independent events. Like I said, there was a whole page on it yesterday. You didn't know that necessarily that they were called that, independent, but you knew that if you had the probability of one event and you had the probability of another event, and those two events, now we know those two events are called independent, you take the two probabilities and you multiply them. Okay, so that's what you did on all those in that worksheet. You multiply them. That's what this formula says here. Okay, so looking at this first one, rolling a die, flipping a coin, we already said those are independent events, so I'm going to find the probability of a 6, which is 1/6, and I'm going to multiply it by the probability of heads, which is 1/2, and I get 1/12. Very easy. Part B. This time we're picking from the deck and we're not replacing, we're picking a second card from the deck, finding the probability the first card is a king and the second card is a queen. Well, this time we said these are dependent events, so the process is just a little bit different. We are still going to find the two probabilities and we are still going to multiply them. So the formula doesn't necessarily change all that much, except that the second probability is not just as simple as figuring out the probability of a queen. Why? Because it's no longer a standard deck if I took a card out and I didn't replace it. Okay, so that probability of B is the part that's altered a little bit. But I do still find the probability of a king, and that's for 50 seconds like it has always been. Okay, I am still going to multiply, but again, now my second probability is affected by the first. So there is one less card because I didn't put it back. And then I have to think about, well, what did we get the first time? We got a king, okay? That does not affect the number of queens, so there are still 4. So it's 4 out of 51. And then I'm going to, of course, simplify on the diagonal if I can, which I can here. And then I'm going to multiply, giving me 4 over, looks like 663. Okay. Now, we did also talk about in class, even though it's not written here, I asked students to find the probability of king for the first and then king again. And we talked about how, again, these are dependent events. I still use 4 over 52, but then there's one less king, so 3, and there's one less card, so 51. And I think this is 1/13 times 1/17. And that gives me 1 over 221. Okay. So that's dependent. All right, next we took a look at page 1 or page 14, the problem at the top, page number 1, and also 4 and 5. So I'm just going to quickly go through those with you. Number 1, and actually 1 and 2 both, are asking you to make an area diagram for the scenario we did the other day with the pencils and the erasers. So if you recall, we made a tree the other day, and we started by the questions, what are the definites or the events, and what are the choices? Well, in this problem, the events are pencils and erasers. The choices are the different colors of pencils and the different colors of erasers. So when we made our tree, we started with the first layer being pencils, and then we divided up the branches between the different colors. And then the second layer was the erasers, and we divided up the branches with the different colors of erasers. Now we're going to make an area diagram. So an area diagram, you still start by asking yourself those questions, and you still decide what are the definites and the choices. In this case, we just said the definites are the pencils and the erasers. So I'm going to put the definites along the top and side of the area diagram. And it doesn't matter what order you go in. I'm just going to put pencils here and eraser here. And now I'm going to divide up the sections of the side and top with the choices. So where the branches go on a tree for the choices, they make up the divisions for the side and top on an area diagram. So the pencils could be either yellow, red, or blue. And so I'm going to look at the probabilities we had. And if you remember, we figured that out the other day. We have 2 out of 6 for the red, we have 1 out of 6 for the blue, and we have 3 out of 6 for the yellow. So that gives us probabilities of 1/2, 1/6, and 1/3. So I'm going to do the half first. I'm going to take this pencil side and I'm going to divide it in half. And I want you to try and be as proportionate as possible. And then I want to label that probability of yellow equals 1/2. Okay, now I need to divide up the other half into 1/3 and 1/6. Well, remember, 1/3 is 2/6, so I want to make it twice as big as the other. So that looks like I've got it in about 2/3 and 1/3. Sorry, 2/6 and 1. Yeah, 2/6 and 1/6. Okay, so we have probability of blue is 1/6, and we have probability of red is 2/6, which is 1/3. Okay, now we're going to do the same thing with the erasers. So erasers is 2 different colors, and like I would be making branches on the tree, I'm now going to divide up the top with the percentages or the fractions here. So 2/3 and 1/3. I'm going to try and think about that in thirds, and I'm going to try and make that one section look half as big as the other. So probability of red was the 2/3, and the probability of yellow is the 1/3. Now we have independent events here, so eraser and pencil, they don't affect one another. So remember, we just multiplied to get the probabilities. So 1/2 times 2/3, looking at the diagonals, gives me 1/3. 1/2 times 1/3 is 1/6. 1/3 times 2/3 is 2/9. 1/6 times 2/3 is 2/18, which is 1/9. 1/3 times 1/3 is 1/9. And 1/6 times 1/3 is 1/18. Now, it should be at least close to being proportionately accurate. The 1/18 should look about half as small as the 1/9. The 1/9 should be about the same size, and the 2/9 should be about twice as big as the 1/9. So that looks pretty good. All right, so now we have our area diagram. That takes care of part 1 and 2. So when you're asked to make an area diagram, that's what you'll do from now on. Then we took care of problems 4 and 5 on the page. 4 is dealing with, this was 1 and 2. 4 is dealing with a 2 jelly bean jars. And it says we're taking 1 bean from each jar. What is the probability you get a purple and a yellow? Well, purple is 60% probability. And yellow, it says in the problem, is 30%. So, whoops. So when I multiply 0.6 times 0.3, I get 0.18. So the answer is 18% for the probability of purple, yellow. Okay. And lastly, number 5, a roulette wheel. We have numbers 0, 0, 0, 1 through 36, and the 1 through 36 are red, and half of them are red and half of them are black. 0 and 0, 0 are green. So part A says, what's the probability of the spin landing on red? Well, hopefully you realize that's going to be 18 out of the 38 slots. And of course, we can simplify that to 9 out of 19. Okay. Next, not red. Well, if it's not red, then it's the rest. So that would be 20 out of 38. And that simplifies to 10 out of 19. And then part C, we want to bet twice on red. So what's the probability it lands on red twice? That would be the 9/19 times 9/19 again. Those are independent events, which gives me 81 over 19 times 19, which is 361. Okay. And that takes care of those two problems. Now, notice we did those problems without making any diagrams. We didn't really need the diagrams because we just needed one probability each. Now, I told the class that as we progress throughout this unit, there will be times where we're going to need a bunch of probabilities, in which case we will make diagrams. And it's going to be important that you know how to make a diagram on your own. So even though we didn't need them and we were able to answer these questions without diagrams, we did kind of talk about how we would make a diagram. So I'm just going to do that briefly here. So back to the one with the jelly beans. If I'm asking myself, well, what are my definites? What are the events? The events are the two jelly bean jars. We're picking from each because it's jar 1 and jar 2. So if I'm making an area diagram, that would mean jar 1 and jar 2. Okay. And that would then mean that I would divide up 60% and 40%, I think it was. And I'm just doing this quickly here, but so I'd have the probability of, I think it was purple is 0.6, and the probability of, I think it was black, is 0.4. And then I would divide up the top for jar 2. Jar 2 was orange, yellow, and white. So orange was half. Orange, 0.5, and then yellow was 30% and white was 20. So about like that. Yellow, white, 0.2, 0.3. Hard to read. Okay, but anyway, and then we would multiply and fill those in. Okay, so that's what our area diagram would look like for that scenario. Just be careful. You don't want to mistakenly make a diagram like this, jar 1, jar 2. The reason that's wrong is because that says jar 1 or jar 2. I don't want jar 1 or jar 2. I want jar 1 and jar 2. So that's wrong. Now, if I made a tree diagram for that scenario, same thing. What are my definites to the two jars? So my layers are jar 1 and jar 2, not my colors. So I want to start with jar 1, and my colors are purple or blue, so I would start it like that. Okay, and now again, what would be wrong would be if I'd say jar 1, jar 2. That would be wrong because that's saying jar 1 or jar 2. We don't want that. We want jar 1. This is my jar 1 layer, purple or blue. Then off of that, the colors, whatever they were, orange, yellow, white. Orange, yellow, white. Okay, that would be a correct diagram. And that second layer that I just drew, that's jar 2. Okay, we also kind of just quickly talked about how the diagram would look for the roulette wheel. So my definites, and you should kind of think about this yourself a moment, what are the definites with the roulette wheel? Well, they are, in part C of the problem, they are the two spins, so spin 1 and spin 2. So if I'm making an area diagram, spin 1, spin 2, that's how I would start it. My choices are either red or not red. So I would divide that up, and I don't even remember what the probabilities were there. They're about 50%. It was about 50-50 actually. 9/19 is almost 50%. But I would divide that up red, not red, and so forth. Red, not red. Okay, it wouldn't make sense to divide it up with spin 1, spin 2, because that's saying either spin 1 or spin 2. That's wrong. Okay, it's spin 1 and spin 2. Similarly, the tree, and when I think about that, my layers should be spin 1 and spin 2. So my choices for spin 1 are either red or not red. And that represents, that layer represents spin 1. So then my next layer, my choices are red or not red. Again, red or not red. And that layer that I just drew represents spin 2. Okay, so that's the correct setup for the tree. And this is the correct setup for the area. And again, these are wrong here. This is my correct setup for the jar tree. And this would be the correct setup for the jar area diagram. Okay, so hopefully that makes sense. Again, we didn't take a whole lot of time to actually make those because we didn't need them to answer the question. But if we were to set them up, that's how we would set them up. Okay, so your assignment for tomorrow is, we actually just finished all of 14, so you don't need to do that, but you do need to do worksheet number 2, problems 1 through 16. Do those for tomorrow.